Thank you. Well, that's my name, Tuck. So I do come from Monash University. Monash University is in the city of Melbourne. First of all, I'd just like to thank Michael for that he had this opportunity to talk to you. Okay, so where is Melbourne? Melbourne is probably at the southern part of Australia. We have wonderful weather over there. And I think we were voted most livable city quite a number of times. We seem to compete with Toronto. So you're always welcome to come and visit us. I'm in the mechanical engineering department. So a lot of the things that I do are actually more of the engineering, physical kind of thing. But more recently, I've been moving a lot to bio-related stuff. So that's my lab, and we have two major research trusts. One's on biochemical analysis techniques and particle cell manipulation. They are not actually mutually exclusive. In fact, there's a lot of overlap, and so that's why we have to develop both arms together in order to get the outcome that we want. Now, for me personally, a lot of things that I do is actually modeled after the wise words of Einstein. It says that things should be made as simple as possible, but not simpler. This is quite a profound statement, I find. And as someone who is building instrumentation and devices, it's helping to guide me along the way. Just as an example, I mean, if you have an instrument which currently operates with 10 mirrors, and I can actually try to make it work with 6 or 7 mirrors, so I've kind of made it work simpler. But it's not really the most as simple as I can possibly do. So it's like you don't do something just for one step. You kind of look at the end, and you're guided to try to make it as simple as possible. And it's quite important for people who make devices, because when you make it as simple as possible, a lot more people will find it far easier to use. It's going to be more robust, and that's the general idea. Okay. So I'll start off by talking about my work in biochemical analysis techniques. And as you know, when you do biochemical analysis techniques, it's always done with a liquid medium. Because things like cells, they require liquid medium to survive. And because of that, in the quest of moving towards the use of smaller volumes, which actually has value, because if you use a smaller volume, you use less of the reagent. Sometimes the reagents are expensive, they're very scarce. We want to use as small as possible. So the general trend in the past has been to shrink things that work in channels, and then to make it to smaller ones. So if you have a flow system, you just try to make it smaller. And that's worked for some time, until they start to realize that when you try to shrink the dimensions, you encounter lots of problems. You have problems in mixing, and you do have problems in clogging as well. Okay, so there's been recently a big rethink on how a microfluidic system should go. And if you look at biochemical analysis techniques, they don't actually operate continuously. They don't work in a continuum. Most of the time, you need a specific volume to react with another volume. So that gives rise to what's known as this field of discrete microfluidics. For example, if you have a droplet, it's a discrete amount. So you get things to react based on fixed amounts. So we are moving in that direction, and actually we find it so much more useful because it simplifies a whole lot more things, as I try to illustrate later. I'd like to also take this point to thank my collaboration with the Cardiovascular Research Institute in Singapore. So quite a lot of things that I do is trying to support what they are looking at. And I'm also thankful to the Australian Research Council, which recently gave us a grant to work on these devices based on this. And the motivation is clear because in Australia we have it's a very vast country, so the rural places get neglected. And one of the things that the government is trying to do to help the people in the rural areas is to lay this fast fiber optic broadband. So the premise is you get medical diagnostics done far easier. But the thing that we're trying to fill in is you can't build an expensive laboratory in these rural places. So what we're trying to do is to create what you call point-of-care technologies that are cheap, affordable, and simple, so anyone who is operating at the outback or rural place can get their work done without needing to send a long distance to laboratories elsewhere. Okay, so one of the things that we've looked at initially was to try to revisit the simple microplate. The microplate, as you know, is just a series of test tubes in an array. So this is the tool of use in screening and so on. Okay, so it's kind of remained the same for a pretty long time. And then now when we're trying to move towards small volumes, we're starting to encounter a problem. So if you made your wall, the well, in a smaller dimension, you then have to dispense into that small dimension, right? And usually this is done using automated systems. So that presents a problem because there's a high chance for the tip to collide with the wall. And then you have damage and so on. So in order to circumvent that problem, then you have to design more precise machinery to do that. Okay? So what we've done is actually try to do a rethink using basic mechanics, and we found that if you put a droplet just right at the top, and if the diameter is small enough, by capillary force it actually gets pulled in by itself. So we've managed to show that with channels that are hydrophilic, and even if it's hydrophobic, when the volume is below a certain size, it's actually going by itself, which then is amenable when we try to make systems that work with small volumes. Okay, and that's of course one way that you can think about it is why do we actually need that channel in the first place? Because you can actually still make use of, let's say, a 96 well channel, like standard microplate well. We've done simulations and experiments, and we find that depending on the wettability of the liquid, it doesn't always fill the entire well. So this is done using computer simulation, and this is what happens in the actual case. Okay. In order to circumvent this, my colleague tries to use low frequency vibration to do it. So he does manage to spread the liquid out, but that's at the expense of quite a complicated system. So we are currently developing methods that don't require that. And it turns out the using of the standard microplates like this has limitations, where our system using capillary wells actually is much better. Okay. So now a lot of the optical analysis is done, for example, using an imaging system. And what we found is with the standard microplate as such, it's actually limited by the point spread function. So meaning if you record at one point over here, you're not necessarily just taking from one point, but you're taking a spread around it. Okay? So if you match the point spread function from a capillary well as compared to a standard microplate, which the shape is actually dictated by the meniscus, we have found that the sensitivity of using the capillary wells is about 2 or 3 times better. Okay. And we have also extended this method to solve a problem in microplate instrumentation that has been around for some time. So two of the major problems in microplate instrumentation is that when you dispense the liquid, sometimes you have bubbles inside. And once you have bubbles and you're dealing with a small volume, it can lead to erroneous results. So the interpretation of the result is wrong. The other thing is sometimes the instrument suffers from pipetting error. And again, if you're dealing with a small volume, the error is actually built up. So with a standard microplate, it's very difficult to detect for these errors. But with our system that we built up, let's say with an angled mirror like this, because we can now image from the side, we can actually pick up the presence of bubbles quite easily, and as well as if you have any pipetting error. That's for an imaging system. We can also apply it on a non-imaging system, which actually gives higher sensitivity, although sometimes with less convenience. So in this case, we have the excitation light coming from the side, so that it interfered from the signal that is going out. This is for fluorescence measurements, and we have also applied it for absorbance measurement as well. In this case, the light actually comes opposite to the detection. Okay. And one of the interesting things that we picked up along the way when we used the capillary wells was the fact that if you lighted one end of a capillary, the one that has liquid in it, you find that the meniscus actually lights up. So this is using a green LED, and this was using the red LED. And that's because of the effect of the light at the interface over here. As you know, when light goes between the refractive, undergoes a refractive index change, you have a lot of light coming out. So we have actually applied this method to measure the contact angle. And the contact angle is associated with the wettability, which is important because in biochemical analysis, you want to keep your wettability consistent. So thus far, there have been no ways to check it whilst it's being used. So our method actually allows us to do that. We're now trying to apply to other methods which require excitation light, because most of the time with normal fibers, you have light coming in, and if you want light to go out at a specific position, you make a cut so that the light leaks out. And they find that that's very inconvenient, whereas in our approach, all we need to do is to move the meniscus to the right place. You get the light coming out. Okay, so the other thing that is useful in biochemical analysis is actually the ability to do mixing. Now, the problem for liquids that are in low volume is the Reynolds number is low, which means the inertial component is far lower than the viscous component. So you can't do things like creating a turbulent flow, which actually helps mixing, or also to create a circular kind of flow for that. So many people in the field have been trying to solve this problem. One of the most famous was the work of Whitesides in Harvard, where he actually created a serpentine channel. So when it flows through that serpentine channel, it can get a mixing to a certain degree. Now, we found that the efficiency of doing that is pretty low, and also it also has that problem of clogging. So we've come up with a very simple approach, which is based on our capillary wells method. So all we need to do is actually to push the liquid out. So when you push it out, it forms a pendant drop, what we call a pendant drop. And because the liquid actually comes out faster on this side, it creates a circulation. So when you pull it back, the liquid, when it comes in, will circulate the other way around. And we found that all it needs is just just one or two times, and we can actually do the mixing. So this is the evidence of it. So we have blue and red dye liquid. So the red component, of course, as you can see, is higher over here. And after we do the process, it's uniform. Okay. So also with this method solve this problem of mixing. And also in biochemical analysis, when you prepare the sample, sometimes the concentration is not at the right amount. And what we do in order to get accurately to that concentration that we want, we do what is known as a concentration process. Okay? So there are various ways of doing it. A lot of times it makes use of complicated methods. So what we found is we can actually push this out, and when you push this out, it has a higher surface area to air contact, and then evaporation takes place. So when you have evaporation, the analyte becomes concentrated. So when it's ready, we just pull it back in. So we do two things at the same time. We mix, and at the same time, we pre-concentrate. So we find that this solves quite a lot of the problems. Okay, and again, if we take a step back to the pre-concentration thing, we do find that a lot of times the process, in fact, we do need to have a manual intervention. When it reaches the concentration that we want, then we pull it back in. Okay, so we realized that actually if we design our wells carefully, we can actually put a larger volume over here, which is lower concentration. So when it starts to evaporate, then the concentration builds up, and when it reaches a small enough volume, it just goes into the well by itself. So we bypass a few steps from that. And interestingly, we also found that if you have that droplet covering a few holes, the number of holes doesn't really affect it. Okay, so my collaborator made a nice simulation video of when the liquid tries to enter the two holes. So first of all, we have a view from the top. So it starts to evaporate and it goes in this way and it fills. And so you have the view from the side as well. So you get it. So essentially, with let's say if we have multiple wells to fill, we don't actually need to dispense one at a time. So we just need to cover the whole area of the drop. When it concentrates to the volume that we want, it just goes into itself. Okay. So the technique that we've developed using the capillary wells is supposed to rival the standard microplate well. Okay. But recently there's also been a movement towards developing biochemical analysis techniques for third world country. And I'm not sure whether you've heard about the Gates Foundation. They give away quite a bit of money if you can help advance health and science in third world countries. So one of the techniques that have been proposed by the White Science Group was to use paper as a substitute for standard microplates. So what happens is you have your standard paper, which is very wetting, so it holds water very well. So if you want to keep it in the certain well, you kind of print wax around that well. So when you put water in, it doesn't spread out. which is very convenient. But the only problem is a lot of the biochemical tests that are sensitive are based on optics, based on light. So when liquid enters into paper, it's almost opaque. So the technique that they proposed to overcome it was to use a bit of refractive index matching using vegetable oil. And there's been quite a bit of criticism of that because then you contaminate your sample and so on. Okay. So what we've done is to do an alternative using basic just transparencies, normal ones that we use in the classroom. So what we do is to create some sort of a silicon surface, which is also very inexpensive, and you paste over it. And if you put the liquid here, as you can see, it holds it just as well. And if the volume is small enough, which is what we normally do, you can actually put it upside down, shake it about, it doesn't drop off. So we make use of the capillary force to do it. And interestingly, we found that the performance of this transparency approach was better than even standard microplate wells. It has to do with the way in which you read, again, making use of the point spread function. So we think that this is a more viable approach if you're trying to do this for third world countries. And actually, it extends beyond third world countries. In fact, there's talk now of if you have troops up front taking part in a war and you want to do biochemical analysis, things like this might be useful. Okay, and as a byproduct of doing it, we've also found that we can make circuits, electrical circuits, which is useful for certain types of biochemical analysis. So the standard way that most people are trying to do now is to use an inkjet printer to print the circuit. All right. However, what happens is it's the tracks, the electrical tracks, can get destroyed quite easily, right? So what we found is if you make grooves and then use the wicking phenomenon, you can actually create a circuit. So this black part here is actually a circuit, is conducting, and then we make some sort of a groove here. These are the two chemicals that we want to mix, and then let's say we apply electrical potential, you can actually do something like electrophoresis. So so when we apply the positive side here, you saw the particles moving that side. You switch the polarity and you can move it back. So you can do things like electrophoresis. Okay, the other thing also we tried to solve was, you see, if you have to remove certain liquids, you either need to use pressure, and what happens is when you try to have pressure in the whole system, you need to use pumps. So it's not uncommon for this system to be small, handling the liquid, but then you have all the other pumps that are real large. So it doesn't quite make sense. So what we found that we can actually pull liquid out from a certain well simply by making use of the surface tension. So this is actually something that is pulled out. This is a small capillary, and this one is the larger one. Okay. And we've also found that although the flow is using the conventional microfluidics is poor because you leave things behind, but you also need to transfer liquid at times. So the way we try to work on it now is, instead of having flow systems, we'll try to make use of discrete transfer. So in this case, what happens is we have the liquid volume over here, and then we try to use a bit of small air pressure using a smaller system to push the liquid out, and we try to do the transfer. Of course, in the process, we found some interesting results, that the gap over here is very important for optimal transfer. Okay. So I had a student build up a simple system like this for illustration. Okay, so we had liquid transfer to the top capillary over here, so we can move it to another one and then try to bring it down. Okay, this is what we transferred down. So the system now is very rudimentary. Of course, it's supposed to do much faster than that. So we're working on it right now. Well, in terms of transfer, another option that we are working on is the use of droplets itself. And even for a droplet on an incline, we found some interesting things. We found that when we put a normal droplet onto some surfaces, we have bubbles forming. Okay? So these bubbles over time will tend to diminish. You see, it's less scintillating right now, so that shows there are fewer bubbles over there. And what we found is these bubbles actually aid in the movement of droplets. So when we have these bubbles being removed, the droplet finds it more difficult to transport. So then we moved on to what happens when you try to create a larger bubble in a droplet. And we found that actually the interesting thing was the reverse action. So if we have this droplet on the incline, and if we put a bubble inside there, we do find that the droplet finds it harder to move now. So it's a strange thing. When the amount of when the bubble size is small, it's easy to move, but when it's large, it's harder to move. And that's because we are interfering with the back contact line. A very good illustration of this effect was a PRL paper not too long ago, which shows that if you vibrate and you alter the contact line, you can actually get droplets to move out and incline as well. However, as far as we're concerned, in terms of transport, the most beneficial way or the most effective way is to use what is known as a superhydrophobic surface. In a superhydrophobic surface, if you put a liquid on it, it forms a ball, and then when you tilt it slightly, it rolls very quickly. Okay, so we managed to develop a way to make the surfaces, and we were actually in the midst of developing the system halfway, and then we read a paper that already beaten us to it. Okay, so we were quite upset that someone beat us to the idea, but we continued to make use of the concept for something else. Now, one of the problems of the pre-concentration method using conventional surfaces like glass is that it leaves behind some residue. Okay, so it's the well-known what you call the coffee stain effect. You put a drop of coffee, and over time you have particles at the edge over here. So this is using a glass. This is a Silanese glass, so it gets smaller. So, but even with a hydrophobic surface like this, which is silicone, we find that you have some left behind. So we moved on to the superhydrophobic surface, and we do find that it forms something like this, and the amount left behind is very, very minimal. Okay. And as a consequence of that, we also, because we could form nice little drops like this, we started to think, could we actually freeze it? Okay. And sure enough, when it froze, it was something like this. So which is quite convenient because it creates a sphere, and then when you thaw it, it also becomes a sphere. Okay. This is we think is going to be quite useful for cryopreservation because the technique of creating a ball like this is actually quite well known, because the way that they do it right now is you have a DUR flask of nitrogen, then you put a droplet, and then when it lands, so it freezes before it lands. That's what we hope. But there's some momentum involved, and so it's not uncommon for when it strikes for it to break. So in our method, we don't have to do it because we've already formed the little ball in advance. Okay? So we are currently studying the cryopreservation of red blood cells, and that's pretty important because some of the cells that are taken from patients are very rare. And when you want to do the biochemical analysis, you only want to use a small amount of it. So our method allows us to do that. Oh, sorry. Okay, so even though we failed to be the first to use the super hydrophobic surfaces for biochemical analysis, we were able to embark on something else, which is to study the effect of liquid on superhydrophobic surface. Because prior to this, in most studies, what happens is they put a high-speed camera and then try to tilt the surface, and then when it moves, then you try to study the dynamics from there. We tried that before, and we find that it's a very difficult experiment to do, and it's not very repeatable because the movement is so fast and you can go out of focus quite easily. So we developed something copying from the atomic force microscope. So if we have a foil, which you can get, a very thin one, the one that we use is just 2 microns thick, and if you have a laser beam reflecting from it, and then you have a rod over here that is wetting. So this is the rod. We put a drop of liquid, and then we have the superhydrophobic surface. So when you move it, we can actually observe what happens over here, the contact angle change. And then more importantly, we can actually measure the force. Okay? And it turns out that the forces that we measure are as close to the atomic force microscope. Okay? So as you can see over here, we're talking about nanonewtons. And we have proof for the first time that the movement, the speed of movement actually affects the force. So we found that when you translate at a slow speed, you have a force build up, then after that it falls off. Whereas if you move it at a higher speed, at 90 microns per second, this is what you typically see on dynamic friction. Okay? And if you have something in between, a speed in between, you have a transition between the two. And we actually found that this is due to the liquid that is drained out from the superhydrophobic surface. When it's fast, you create the air cushion inside superhydrophobic surfaces for a longer period of time. Okay. We also found some strange phenomenon. We actually found that if you create a bubble on the superhydrophobic surface, they actually grow larger than what is predicted in theory. In fact, it was quite impossible to create this kind of thing, and we actually accounted for the mechanics as well. This is one of the things that my colleague did on measuring the contact angle. Okay, so whilst we were disappointed not being the first people to have a system of transferring liquid with very little loss using superhydrophobic surface, we did come across something else which we think might be better. Okay. And this is base. I have to close this because somehow I couldn't embed the. Okay. All right. So if you have a bath of liquid, and if you put some droplets onto it, and you vibrate it at the right frequency, we do find that it just bounces on forever. Okay. If you want to see it again, the first time I saw it when my student recorded it, I just couldn't stop looking at it. So the premise is there is an air cushion over here that when it falls down, it never gets drained off. So, and then when you have the upstroke, it just goes up again. Okay? So, however, there seems to be some controversy regarding the mechanism. Because when you think about it, what is actually liquid and what is actually gas, because both of them actually have molecules inside. And when you bring it really close, do you actually see some liquid transferring across? And that's important for us in biochemical analysis, because now I want to have something that have very little loss to the surrounding. Okay? So right now, what my student is doing is we are trying to fill the bath with a high concentration of fluorescent particles, and we see whether with the bouncing it actually transfers across. If it transfers across, we should be able to detect that. Okay, so this is ongoing for us. And if you think this is a bit strange, this might even be a bit more strange. Okay, so if you have these two droplets over here, when they come together, all right, so they eventually do merge. As we would expect, if you have two droplets on the table, then it will merge eventually, right? But if you notice over there, they kind of bounce a little bit off before they merge, okay? And we found that sometimes you have even something that is a bit more weird happening. Okay, so we have the two droplets here. Look at that. And my student had one recording, it just went on for hours. Okay, so we're still trying to understand this, and we think that this might be something that we can use in our studies as well. Okay, so that's basically our work on biochemical analysis, and I'm running out of time. We've also gone on to particle cell manipulation as well. And we try to use systems that are simple. A very simple system that we developed was a cover slip, simple cover slip with a glass slide. We seal on the sides and leave the side open. We put a droplet here, and due to the capillary that is formed, we can actually move particles from over here to the other side. Okay. We've extended this to an application for a collaborator in the Faculty of Medicine. So they wanted to, so they have adherent cells over here, which they dislodge using the laser beam catapult. And once it gets dislodged, they want to collect on this end to do further tests. So we found that this system is so simple, we just put a droplet over here, the thing just flows over to the other side and gets collected. Okay. So just move on quickly. We also investigated what happens if you have particles floating on the surface, and we found that if you have a droplet, it merges, and then we cause this particle to drop. So we can actually have a system where you have particles, and then we can select the one that you want by just dropping the droplet, and then we just collect the one. Okay. So this is done with this work was done with a single particle. We have also been able to do it with a cluster of particles. And for particle cell manipulation, again, the subject of a grant awarded by the Gates Foundation was biochemical analysis that is done by having the analyte reacting with nanoparticles. So it gives off a certain color, and then it's supposed to indicate the presence of a certain condition and so on. So an easy way to create the pattern of nanoparticles is actually to use what is known as the coffee stain effect. So we tried using it and then found that on different surfaces you actually created different types of ring. And if you use different types of particles, you also develop different types of rings. So we found that the use of polystyrene is probably the best. So now again, we took it a step further, and said that if you want to make this process that is usable in the field, it has to be quite fast to do. Okay? And the evaporation process actually takes some time to complete. So can we hasten the process up? And so what we did was we had a tissue inserted after a period of time, and then to draw the liquid out. But it seems that there's a liquid bridge formed over here, and then it forms a second ring, which is not useful. So we are currently developing this process using a liquid torus. So rather than a droplet itself, we're trying to make a torus ring with a hydrophobic core. And that seems to improve the situation a lot. Okay. We've also made some inroads to try the use of optical forces, and that's part of the reason why I'm here. We found that the basic laser tweezer is well known. You have a particle, then you have a focused beam, and then the gradient force is bigger than the scattering force. You can hold the particle and you can move it. Right? But we found, and in fact literature has shown, that when you focus the beam, if you're handling cells, there's a high chance of photo damage. So we were exploring, do we actually need to use the focus position? Can we actually use the scattering force instead? And it turns out, if we change the axial focus position, if you move it below, you have a different outcome. You move it above, there's a different outcome. Yeah. So this is when the beam focus is above the particles. So that's the center of the beam. So this effect, I think, is quite well known. You do draw the particles inside. It looks out of focus because it is. So now if we move the focus below, and if you see, if you chase after the particle, it goes away. So essentially what we are now working on is some sort of optical stirring method. When we've tried to as you know, in a bioreactor, you want to keep the cells healthy by moving them around. When cells move around, the shear flow actually keeps them healthy. We've tried to use acoustic forces to do it, but they're very strong, so it's not a gentle kind of thing. So it swirls and so on. So we think that this is the better method, because if you can create a multitude of beads and you move it around, it's almost like putting your finger there to stir. And because we're not focusing the light, it's actually much better. Okay, so just bear with me a little bit more and I'll finish. Now, I started off showing a picture of Einstein, and I think it'll be a bit of an insult to finish off without talking about Einstein. So in 1905, Einstein produced 5 major papers. All of them were seminal work, and one of it was actually on Brownian motion. Okay? Brownian motion actually comes about because the atoms and molecules at that length scale will collide with a particle and it moves it around, which is a nuisance for us, because now we can't control things very well, especially when you get down to nanoscale. The Brownian motion will move it around. So we did some investigations on this, and we were wondering if the shape of the particles makes a difference. So the initial work that Einstein and Smoluchowski did was using spherical particles. But later on in 1934, this person by the name of Perrin, he did calculations and found that if you have a rod, the Brownian forces will cause the diffusion faster in this direction than this direction. Okay, and of course you also have the rotational diffusion affecting the whole thing, which in a spherical particle it doesn't, because it's homogeneous in shape. And amazingly, no one did the experiment to verify that until 2006. There was a paper in Science by a group in University of Pennsylvania that managed to get it done. So we were wondering if we could suppress the Brownian motion using this rods instead. And it turns out that when the rods get close to the surface, we found that the suppression was greater in this direction. And we published a piece of work. And later on, that same group that published a science paper cited our work, and they actually explained the phenomenon with using more careful experiments. So basically, it's more of a hydrodynamic behavior. So when it gets close to the surface, the flow in this direction will suppress more than the flow in this direction. Okay. So then we also went on to actually it was quite an accident actually. My postgraduate student was doing this recording of what happens when it comes down to the surface, and we saw this funny behavior when it lands. It lands this way and it started to move like this. It tethered on this head, and so very seldom you get it coming to the bottom of the surface and sticks like that. It will start to touch one end and it starts to move like this. So we were wondering whether we could use it for something useful. And indeed, we did. So we're trying to harness now Brownian motion to tell about the microenvironment. See, let's say if you want to measure the temperature or viscosity at a particular place, some people have actually put these spherical particles inside and see how they move about. That's great because it tells information, but the problem is the particle can actually get out from your field of view. Then you have to wait for another particle to come. Well, of course, you can say, well, I can actually put more particles inside there. But then they start to collide with each other. Then the mechanics becomes a whole lot more complicated to try to solve. Okay? So we reckon that if we could somehow hold the particle within that field of view, we can keep it measuring all the time. Okay? So first of all, we thought that this tethering would work. But again, we found out that it doesn't work very well. Because of the nature in which it turns, it doesn't actually give consistent results. So we haven't conducted the experiments yet, but we started off with computer simulations. So if we have a cylindrical pillar which creates an attractive force, then we wanted to see what is the effect that it will have on the movement. So this is the simulations that were done. So if we use a strong enough force, strangely it doesn't hold the particle fixed. So this is what it will do. So if we use a weaker force, so it drifts off. All right, so we have actually found a scheme to do this. So lastly, I would like to say that another thing that we're trying to investigate is actually based on an interesting work that appeared in Nature Nanotechnology recently. I'm not sure if you know about this field of targeted drug delivery. So they want to now have drugs embedded inside carbon nanotubes. So when you get close to the cell, you get the drugs coming out. So instead of having, let's say, cancer drugs landing up in a healthy cell, you can actually try to land it on the cell that is cancerous, and the action is only on the cancerous cell. So one of the ways to do it is actually to embed the nano drugs within the carbon nanotube itself. So that's been known for some time, and people are working on that. But recently it has been found by this group that when the cell goes over here and the nanotube comes in, quite a lot of times it lands up this way. All right? But They also found that you also have a situation where it gets impaled. It gets stuck like this and the cell dies. And so they were trying to explain that. Now, the problem of working at the nanoscale is because there's really no instrument to look at it real time. So they could only guess what mechanism it is that causes it to do the impaling. And the mechanism that they claim that's working is you have a cell like this, so when it lands up, because the end of the carbon nanotube sees a spherical end. The cell sees a spherical end of the carbon nanotube. It sees this and then it tries to turn it around and then it breaks it down like this. Okay, so using a sphere to enter into the cell is actually quite well known. They've done it many times, and so they're trying to relate the two, and they feel that is the mechanism that's causing it to do it this way. And I saw the simulations that they've done for that, and I think the problem is they did not include Brownian forces. And based on what we saw previously, any particle would not land like this. They would actually land on one side. Okay? One end will touch first. So when it lands, there is still Brownian motion. And we believe that because the Brownian motion is stronger in this direction, it will actually pierce. And once it pierces, the cell would do the rest. You will bring it around like this and then get impaled. So we're working on that model right now. So it turns out that we're going in directions that we didn't expect to. And that's a nice thing about research. Okay, so I'll just end it there, and be glad to take any questions.
So when you were working with the bouncing
droplets,
that's just water.
We used oil. Yeah, silicon oil, which is useful because let's say if you're transferring, let's say, cells, it's better to use oil because the hydrostatic thing, you put water, it actually does the cell. Yeah, but we found that the viscosity actually does play a role. In fact, the bath itself should have a higher viscosity than the one that's bouncing on it. And we found it to be more effective at investigating why. The other interesting thing that we found was, in fact, the initial experiments was using quite a significant depth of bath. So we thought that if we are building a device, do we actually need that much of liquid? So then we started to drain and drain and drain. And we found that you only needed something like 40 microns thickness in order for this whole thing to work. So, which is great. So now we can actually make systems far easier using 40 microns of liquid rather than a few centimeters of liquid, you have spillage and so on. So with that 40 microns, we saw that if you have a sufficiently wetting surface, you can actually put it upside down. It's fine.
So the idea of that system like just mix the droplets or whatever?
It's in transport. So because you usually need to transport after you do a process, then you've got to transfer to another site to do something else and do something else. I must say that watching a bit of movies kind of stir your imagination. You watch the Incredible Hulk. He moves, and after a while he runs and he decides to jump. Then he jumps further. So we're thinking now that it starts to bounce. What happens if you apply a certain force? It actually bounces it. Yeah. Yeah. That's it. All right. Thank you.
someone to meet with now, or?
No, not for today.
Okay.
I'm waiting for the AT guys to come because I'm not touch anything until
Oh, okay. Fine then.